Hey there, Don. Hey, just hang in. You can sign in and bring up your midway quiz right here. Good. All right. All right, folks. So, what is the solution of adding all the numbers 1 plus 2 plus 3 all the way up to 100? Does anyone have the solution, Brandon?
5,050.
It sure is 5,050. And how did you come up with that solution?
Because when you add each n number, it's going to be 101.
Yeah, if you add 1 plus the 100 at the end, so that's 101. And then 2 plus 99, that's 101. And 3 plus 98, that's 101. And you can imagine going all the way down to the middle, adding each pair of n numbers as you work your way in. How many pairs will there be?
50.
How do you know 50?
Because there's 100 numbers and divide by 2.
Yeah, that makes sense. You've got 100 numbers, and if you put them in pairs, then you have 50 pairs. And so if each pair adds up to 101, and there's 50 pairs, then that gives you 5,050. A very nice, elegant solution that doesn't require actually typing it all into your calculator. The story goes, this sequence is famous because there was a mathematician who I believe he was in the 1700s. His name is Gauss. And he, I think, was like a 5 or 6-year-old boy sitting in a math class. And the teacher needed to buy some time. Who knows, maybe the teacher needed to leave the room or who knows what. And the teacher said, hey, everybody, go ahead and add together all the numbers 1 plus 2 plus 3 up to 100. And the teacher figured it would take them all a while because they'd all be sitting there adding them up. And Gauss, within minutes, stood up and went to the teacher and said, I'm done with the problem, now what should I do? And he used that same strategy of adding up each pairs of numbers. Anyway, he was a child prodigy, and he went on to be a great mathematician. Okay, so that's the first one. How about a half plus a fourth plus an eighth plus a 16th plus a 32nd? What does that add up to? Did anyone try it on a calculator? Just to see the approximation of what it was adding up to? I wonder, does this computer have a calculator? I don't know. I think I'll use Google. Google is a calculator, right? Google calculator. Boy, that just took me right to big. I wasn't okay with that. Okay, so 1/2 plus 1/4. Well, I'll start one at a time. So there's 1/2 plus a fourth plus an eighth plus a 16th plus a 32nd plus a 64th. What are my numbers approaching? Plus 1 128 plus 1 256 plus 1 512. Yeah, what are my numbers? Do they seem to be approaching anything? Plus 1024. Yeah, it seems to be approaching 1. We're working towards 0.999. And if I were to keep on going like plus 1 2048, there's still 0.999. Plus 1 4096. I'm trying to get to 0.999. Anyway, it appears to be approaching 0.99999. So how can we understand this idea that if you add up infinitely many things, that they're eventually going to add up to 1? Does that seem reasonable? Do you think it'll ever actually equal 1? Or do you think it'll just add up to 0.99999? 9. Maybe just 0.99999? Well, even if it did add up to just 0.99999, I wonder if that still is equal to 1. Well, first of all, I want to show you a simple visual graphic for this. If you take a square, just a simple square, work with me and pretend that that's a real square. Then what I'm going to do is take half of it and shade it in. So that represents my 1/2. And then I'll take 1/4 of my square, which would have been this piece right here, and I'll shade that in. So now that's accounted for. And then if I cut all of that into eighths, which I suppose I could do by just cutting it this way, then I would go ahead and shade this in. And then if I wanted to cut it into 16ths, I would have cut it into 16 pieces, and then I could shade that one in. And that takes care of 1/16. And you can see what I could just keep on doing. I could just keep on cutting my square into smaller and smaller fractions, and then shading one of them to account for the next one. And I'll go ahead and do that for the 64th as well. I'll cut it into 64ths, and then shade one of them. Well, my shading process here doesn't really demonstrate it very well, but I was kind of going in a spiral. That definitely was not obvious, by the way. I did it. But you can see that I'm heading towards this piece. Now, if I just keep cutting that in half and shading in half, what will happen in the long run? So I cut that in half, shade in half. Then I cut that in half, shade in half. Cut that in half, shade in half. Cut that in half, shade in half. What will happen in the long run? It is a little bit of a spiral shape. And how much of the square is going to end up being shaded in?
You just keep.
Well, now that's an interesting point. It'll never be completely shaded in, right? At any one point along the way, it won't be completely shaded in. I would still have a little teeny gap in there that's not shaded. But I'm asking, what if you do keep doing this process forever? If you do the process forever, will the whole thing get shaded in? Oh, Angel is shaking his head no. Well, here's a thought experiment. If you claim that it will never get shaded in completely, I could disprove that by saying, pick one point on this square that you think is never going to get shaded in, right? So let's say I hadn't gotten that far in the process and I was still like right here. And you said, no, it's never going to get shaded in. There's still going to be stuff that's not shaded in. And I said, well, you pick one point that's not going to get shaded in. And you say, I think that point is never going to get shaded in. But then I could, in a finite number of moves, go about shading in half, and then half, and then half, and then half. And eventually, in a finite number of moves, I will have shaded in the point that you said would never get shaded. And in that way, no matter which point of the square that you claim will never get shaded, I can, in a finite number of moves, go ahead and shade over it. And therefore, any point you claim that will be unshaded, I can show will be shaded in a finite number of moves. And that's a clever workaround to the idea that if you add up infinitely many terms that equals 1, by showing that after any finite number of moves, I can shade in any point that I want. Yeah? Well, okay, so I guess the real point is that sequences are tricky. Sequences are tricky. Before we do the formal lesson here, I'd like to consider this number, 0.99999. Everyone, have your packet open. And you're all at section 7.1 right now. Go ahead and we're going to do a little proof right up here at the top. Right up here at the top. I ask you all to go ahead and write down point 99999 ... equals. Now this might sound theoretical or just like some YouTube video, wondering what is 0.99999 equal to? Well, first of all, does anyone have a guess? Do you think it's equal to 1 or is it just less than 1? If you wrote 0.9999 with infinitely many nines, would it be equal to 1? Because it's so close, it's there. Or will it always be just less than 1? What do you think? Especially on a number line. If I were to draw a number line, and definitely here's the number 1 and here's the number 0, where would I put the number 0.99999? Would I put the number at 1? Or would there be a dot just ever so slightly to the left of 1? What do you think, Jacinda? Slightly to the left? That's a very reasonable thing to say, right? Anyone else have a feeling about 0.99999 repeating forever? Is it equal to 1 or is it just to the left of 1? Say, what do you think? Aldo, what do you think?
It's
Not 1, it's just less than 1? Alejandro, what do you think?
less than 1.
Less than 1, Luis?
Yeah.
Yeah? Brian? Yeah? Angel? Xavier? Not sure? Mishkumar?
I won.
Maybe 1? Okay, got one potential believer here. Carlos? A little less than 1? Brandon? Okay. Okay, so I suppose the first thing I should do is, what evidence would I have to give you to convince you that it actually is 1? Is there anything that I could say up here to convince you that it's actually equal to 1? Or no matter what I say, would you be like, whatever, Mr. G, it's less than 1? That's an interesting idea right there, is what do we accept as evidence? As humans, going about our lives, talking about things that are political, climate change, there's all sorts of big issues that we talk about. What evidence would I accept to change my mind? Well, I hope that I'm about to change your mind. So everybody, did you all write down 0.999 ... equals? Let's just say we don't know what this equals. I have no idea what it equals. What should I say that it equals? When you don't know what something is, what do you write down? A question mark or a variable x. I'm saying, hey, I don't know what that is. So I'm just going to call it x. And now we're about to do some clever algebra, and we're going to solve for x. So what I'd like everyone to do is go ahead, and keep in mind this is valid algebra, multiply both sides by 10. Just go ahead and multiply both sides by 10. If I multiply this side by 10, obviously I get 10x. And if I multiply this side by 10, what do I get? What's 10 times 0.99999? 9.99999. Equals 10x. Okay, well, we haven't done anything too magical yet. We've just multiplied by 10. But now, using the ideas that we did with solving by elimination, I'd like to go ahead and take this equation, 9.99999 equals 10x, and subtract the equation 0.99999 equals x. These are two legitimate equations. I claimed, they're true by assumption. We're saying 0.999 is equal to something. And if I multiply both sides by 10, I get a new equation. And I've got now two equations. I'm going to subtract them. But what happens on the left-hand side when I subtract 9.99999 minus 0.99999? It's just 9, right? All those 9s cancel out, all infinitely many of them. And what happens on the right-hand side when I subtract 10x minus 1x? You get 9x. And now, finish solving for x. X is being multiplied by 9, so you divide by 9, and what do we get? X definitely equals 1. Are any of you convinced? Because I'm telling you right now that the mathematical community on planet Earth all agrees that 0.99999 is equal to 1. It's not just to the left of 1. It's not just less than 1. It's definitely equal to 1. That's what human beings on planet Earth currently believe. Mathematicians, that is. So there is agreement that 0.99999 is 1. It's not just the left of 1. It's actually there. Now that's weird. That's weird, right? Do any of you still not believe me despite this algebraic? And that's fine if you don't. That's fine if you don't. But I encourage you, if you're going to say, yeah, I see what we did, x is 1, 0.999 is equal to 1, I still don't believe it, I encourage you then to find the flaw in the argument. If you think that this is just magic and hocus pokery, that's really not true, then what did we do that was not valid? All right? Okay. Well, that's my introductory skit. That's just to get us warmed up and ready to go. So we're going to go ahead and take a look at these sequences. So we're in section 7.1. Let's go ahead and take a look at how we're going to talk about sequences. We have notation, and it's relatively new. That is, at first glance, you might not be familiar with it. So let's all look at number 47. It says here, write out the first 5 terms of the sequence, and they give us this formula. Everyone, I want you to write it down in your own writing. This says A sub n. It's a subscript. So as you know with a subscript, it's going to be A sub n, a little tiny one, equals regular 3n minus 1. That's a subscript, just like log base 2. Log base 2, log base 10, log base e, that was a subscript. This is a subscript. So A sub n is equal to 3n minus 1. Okay, that's the formula. I suppose there's something I should say before even we do this. And that is, if we want to talk about a sequence, like, take the sequence 1, comma, a half, comma, a fourth, comma, an eighth, that's a sequence. What we can do instead is refer to it as A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, and so on. That's how we're going to refer to sequences. We use the letter A. That's just standard. And the subscript tells you which term in the sequence you're talking about. So that's the first term, the second term, the third term, the fourth term, the fifth term, and so on. So this is our notation. Whenever we want to talk about a sequence of numbers, we're going to refer to it with A subscript. Okay, so this sequence, I'm telling you that this represents a sequence. You don't see the obvious sequence of numbers yet, but it represents a sequence. And what we're going to do is go ahead and calculate a sub 1, a sub 2, a sub 3, a sub 4. So go ahead. What we're going to do is replace n with 1. So a sub 1 is equal to 3 times 1 minus 1. You're just replacing n with 1 if you want to find the first term. And so 3 times 1 is 3 minus 1 is 2. That means the first term in our sequence is 2. What's the second term in our sequence? You go ahead and put 2 in for n in both spots. So 3 times 2 minus 1. 3 times 2 is 6. 6 minus 1 is 5. So the second term in our sequence is 5. And so on and so forth. We can go and say the third term in our sequence is 3 times 3 minus 1, which is 9 minus 1, which is 8. And likewise, a sub 4, that'd be 3 times 4 minus 1. The fourth term in our sequence is 12 minus 1, which is 11. Now the instructions say to write out the first 5 terms in the sequence. So I'm going to finish a sub 5 is equal to 3 times 5 minus 1, which is 15 minus 1, which is 14. So folks, now that you've just done this calculation, you might go ahead and take that sequence and just write it out in a natural, intuitive way. You'd say, oh, that sequence. You say, okay, that's 2, 5, 8, 11, 14. Without using the formula, what's the next term in the sequence? What is it? Is it 17? How did you know it was 17? Because it looks like we're adding by 3, right? So to go from 2 to 5, you add by 3. From 5 to 8, add by 3. 8 to 11, add by 3. 11 to 14, add by 3. 14 to 17, you add by 3. So sure, at this point, you could just keep on going. And you could say that this sequence is defined by add by 3. Right? And in that way, you can just keep going. The fact that this sequence is add by 3, how does our formula capture that? What part of our formula now makes it obvious that we were adding by 3? What part of the formula makes it obvious we're adding by 3 every time? Adam? What part of the formula 3n minus 1 makes it obvious that we were adding by 3 every time? Yeah, the 3n. Because the 3n states that for every number that you plug in, you're actually adding an additional 3 to the sequence. Okay, so folks, this is how we represent a sequence. We have a formula that tells us how to calculate every term in the sequence. And this is called an explicit formula. The formula will explicitly tell you any term in the sequence. So for instance, this next sequence, number 48, the sequence is determined by n squared minus n. Now before we actually calculate that, can you tell just by looking at this formula how much we're adding by every time? You know, in the first one, 3n minus 1, in retrospect, we could say, oh, well, sure, it's 3n, so we're adding 3 every time. Can you tell how much you're adding this time? No, you can't. So let's go ahead and explore it. Let's just find out. A sub 1, go ahead and write out the first few terms. In fact, go ahead and do the first 5 terms. Go ahead and calculate the first 5 terms. So it'd be 1 squared minus 1, 2 squared minus 2, 3 squared minus 3, 4 squared minus 4, and so on. Go ahead and calculate it. That sequence. Oh, oops. So walking around the room, it looks like a good deal of you got the sequence 0, 2, 6, 12, and 20. 0, 2, 6, 12, 20. So writing that out as a traditional sequence, 0, 2, 6, 12, 20. What's the next term? Without looking at the formula, what's the next term? You're going to claim 30? Is it 30, folks? I don't know. What do you think the next term is? Anybody else, or are you all saying 30? Me, Kumar, what do you think? 30? And how did you get 30? It's going up. So you went up by 2, and then up by 4, and then up by 6, and then up by 8, and then up by 10. Okay, I'm convinced. That seems very reasonable. So the next term would be 30. Now, if you have this rule, plus 2, plus 4, plus 6, plus 8, plus 10, how could you now tell me immediately what the 10th term is? If I asked you for the 10th term, or even worse, what if I asked for the 50th term? If I asked for the 50th term, would you want to continue doing this method? Plus 10, plus 12, plus 14, plus 6. No, that'd be terrible, wouldn't it? That'd be terrible. And so, again, that's why this formula right here is called explicit. It's an explicit formula. AN equals n squared minus n. It is explicitly telling you any term in the sequence, and you can just go straight there. You don't have to count all the way there to get to it. That's what we mean by explicit. Is there another way to generate that sequence other than plus 2, plus 4, plus 6, plus 8, plus 10? What if I told you that's not correct? What if I said, actually, that's not how this sequence is generated? Is there another way to go from each number to the next? What's that?
I imagine so.
Yeah, I mean, probably. I mean, I suppose we could just say, sure, why not? There's probably lots of different ways to do it. But what could be a way right now that you can see? Oh, well, actually, I don't. It's not obvious. Because adding seemed to be the way to go. Multiplying doesn't make much sense. To go from 0 to 2, you don't multiply by anything. From 2 to 6, you multiply by 3. From 6 to 12, you multiply by 2. From 12 to 20, you multiply by a fraction. That doesn't seem very reasonable. Well, just to show you another way to think of this, can we factor n squared minus n? Can you factor out the GCF? How can I rewrite n squared minus n? It could be n times n minus 1. Well, what does that mean? What does that mean? If it's n times n minus 1, I'm going to look again at this sequence. N times n minus 1. So it'd be 1 times 1 minus 0. And 2 times 2 minus 1. Oops, sorry, minus 1. And then 3 times 3 minus 1. And 4 times 4 minus 1. And so on. So that's really 1 times 0, or 2 times 1, or 3 times 2, or 4 times 3. Do you see what the potential pattern is? So like, for instance, the 5th term would be 5 times 4. Go ahead and tell me, what would the 50th term be? If the 4th term is 4 times 3 and the 5th term is 5 times 4, the 50th term is? What was it? Is it 50 times 49? Yeah, that's another way of looking at it. You could think of it as a product, 50 times 49, rather than, 50 squared minus 50. Does that really end up giving you the same thing? Is 50 squared minus 50 the same as 50 times 49? Yeah, I like that, probably. Yeah, probably. Yeah. All right, so folks, that's it for explicit sequences. I'm going to leave those next two for you to do. To write out explicitly the first few terms in the sequence. So let's keep going here. The next section is just to get us to consider infinite sequences versus finite sequences. How can you tell the difference between an infinite sequence and a finite sequence? What's the giveaway for the first two? Because of the ellipse, the dot, dot, dot. Is that E-L-L-I-P-S? Is that? Or is it ellipsis? What's the technical phrase for that when you have dot, dot, dot? I think it's ellipses. Yeah, the ellipses means that it goes on forever. So this is an infinite sequence, whereas this is a finite sequence because it just stops. These two were obvious because of the ... ellipsis giveaway. What about these two sequences? What's going on here? Now this is actually very different because we haven't seen this notation yet. But just taking a look here, they're saying, what does a sub 1 equals 5 mean? The first term is 5. And then they're saying, for all the values of n between 2 and 50, do this formula. Now, even though we don't even know what this formula means yet, the fact that you're only doing the values of n between 2 and 50, is the sequence going to be infinite or finite?
Finite.
Just finite. And I should say that we assume that n is always the counting numbers. I should have said that right away. N takes on the values 1, 2, 3, 4. We're talking about integers. We use n to count through the integers. Count through integers. All right, whereas for this next sequence, the first term is 8, and they're saying go ahead and do the sequence for all terms starting at 2 and above. So then this sequence would be infinite because you're doing all the values of 2, 3, 4, 5, and up to infinity, whereas this one was just finite. So we just want to keep in mind that some of our sequences are going to be infinitely long, and some of them are going to be finitely long. Okay, so we saw an explicit sequence, and believe it or not all sequences are given by an explicit sequence. And before I even give you, before we even do these, I want to give you a famous non-explicit sequence, and that sequence is the Fibonacci sequence. Perhaps you've seen it. I'm just going to go ahead and start writing down some of the terms. I'll do it over here because it's brighter. So it's 1, 1, 2, 3, 5, 8, 13, 21. How am I getting each next term in the sequence? Let everybody have a chance to look at that real quick. How do you get the next term in the sequence? In fact, what is the next term in the sequence? What would the next number be?
Adding the first two terms? Or like adding the terms of 4 to?
Morning, Eddie.
Like if you start with 1, then you add 1, you get 2.
Yeah, 1 and 1 and 2, and then 1 and 2 is 3, and then 2 and 3 is 5, and 3 and 5 is 8, and 5 and 8 is 13, and 8 and 13 is 21, and 13 and 21 is?
30.
Yeah, 34. So that would be the next term in the sequence. Now, that's not an explicit formula. Telling you to add the 2 previous terms in the formula, that's not an explicit formula. If I told you now, find the 50th term in the sequence, how would you do that?
Write it out.
You would have to add, to get the 50th term in the sequence, you'd have to add the 48th term plus the 49th term. Right? To get the 50th term, you have to add the 2 previous terms before it. But do we know what the 48th term and the 49th term were? No. In fact, to get the 49th term, you'd have to add the 47th and the 48th term together to get the 49th term. And to get the 48th term, you'd have to have previously added the 46th plus the 47th term together. And so with a recursive sequence, you start this regress where you have to go back all the way to the last time you actually knew something, and then you'd have to add your way all the way there. So this sequence is unfortunate because there's not an explicit formula. Well, there is actually an explicit formula, but for the sake of right now, we're just talking about the recursive formula. So with a recursive formula, so everybody right up there is the word recursive, we're talking about defining the term of a sequence in terms of other terms in the sequence. So the way, everyone please go ahead and write this down. Write down 1, 1, 2, 3, 5, 8. Go ahead and call it the Fibonacci sequence. And let's write down the formula for it.
It's called recursive.
Right, this is recursive rather than explicit. Explicit means you can explicitly calculate any term you want. Write that. Recursive means you can only calculate a term by knowing previous terms. Thank you, Xavier. That'd be good to write down. Recursive means calculate a term in terms of, that's a terrible abuse of language, previous terms. Oh, that's awful. I'm using the word term in two different ways. But yeah, in a recursive sequence, you calculate any given term that you're looking for by looking at the previous terms that you already have in the sequence.
Also call it implicit? Or was that like, that's something different?
Oh,
You
explicit versus implicit?
Because I thought you mentioned implicit earlier.
I don't know that I did. I said explicit. The other one was explicit. You could call it implicit, I suppose, but I think normally I hear recursive. I like the idea of calling it implicit. Okay, so folks, how would I define this sequence? This is how you would define the sequence. Write it down with me once and then consider it. The nth term in the sequence, okay, that is any given term, just like we were doing previously. Previously, I said something like the nth term in the sequence is equal to 3n minus 1, or the nth term in the sequence is equal to n squared minus n. We're writing a formula for the nth term, meaning any term you like, you can go ahead and calculate it. So a sub n technically means the nth term for whatever term you want to calculate. So for the Fibonacci sequence, the nth term is equal to the term before n, the n minus 1 term, that's the one just before it, plus a sub n minus 2, 2 terms before it. That's the recursive formula for the Fibonacci sequence. That if you want any given term, you add the term before it and the term before that. And actually, there's one more thing I want you to write down. I'm sorry. I feel like I'm doing this a little out of order. What I should really say right now is consider any given sequence. So a sub 1, a sub 2, a sub 3. And if you just keep going, eventually in this sequence, you could get to a sub 50 or a sub 100. But more importantly, you'd get somewhere to a sub n. All right, we're just saying that a sub n is some term out there. It could actually represent a sub 3 or a sub 5, but we're just saying use the word a sub n to represent any term in the sequence. And so if a sub n is called the nth term, then the term before it we represent by a sub n minus 1, and the term after it we represent by a sub n plus 1. And that's just a formulaic way of saying that if you're looking at any given nth term, a sub n minus 1 means the previous term, the one before the nth term. But if we say a sub n plus 1, that means the next term. There. So that's our notation. That's how we refer to any given term in the sequence. So the first, second, third term, the nth term, the previous term before the nth term, and the next term after the nth term. That's how we refer to it. So now that we have these definitions, let's consider number 55, the first recursive formula that you were given. And let's write it again in our own handwriting. We're saying that the first term is 9. And then we're saying that any given nth term is equal to a sub n minus 1 plus 6. Well, what does a sub n minus 1 mean again?
The term before that.
Yeah, the term before it, as in the previous term. So if I want any given term, I look at the term before it and I add 6. So that means a sub n, the nth term, you calculate that by looking at the previous term and adding 6. That's what that would mean. So for instance, using the formula of a sub n equals a sub n minus 1 equals 6, what if we go ahead and let n equal 2? What would I do in my formula? If you say, I want the second term, I let n equal 2, I would write down a sub 2 equals a sub 2 minus 1. That's a sub 1 plus 6. So what does that tell us the second term is equal to? The first term plus 6, which is really, since the first term is 9, 9 plus 6, which is 15. And then you keep going like that. What's a sub 3? What's the third term? Plugging in 3 for n, you would have a sub 3 and a sub 2. So a sub 3 is equal to a sub 2 plus 6, meaning the third term is equal to the second term plus 6. And what was the second term? We just calculated it? 15. So that's really 15 plus 6, which is 21. So what about the fourth term? The fourth term, according to the formula, the fourth term is a sub 4 equals a sub 4 minus 1. That's a sub 3 plus 6. So the fourth term is actually the third term plus 6. So we would say, well, the third term was 21, so 21 plus 6 is equal to 27. This is how you generate a sequence recursively. And that's why we use the word recursive. It recurs. You have to over and over and over again look at the term before it in order to calculate the term that comes after it. So go ahead and write out the first 6 terms. That is, go ahead and find a sub 5 and a sub 6 using that same process. Ryan, what was the fifth term? Yeah, so the fifth term is the fourth term plus 6. The fourth term was 27, and you add 6, and that's 33. Thank you. And then what was the sixth term? Amy?
39.
Yeah, 39. You take the fifth term and you add 6 to it, and then that would be 33 plus 6, which is 39. Now, at this point, you might say, well, Mr. G, this formula is very easy. We're just adding 6. We've already seen a sequence where you just keep adding things. Like this sequence is 9, 15, 21, 27, 33, 39. And so clearly we're just adding 6 every time. Couldn't we write down the explicit formula for this? What would the explicit formula be? Instead of looking at this recursively, saying to get the nth term, add 6 to the previous term, what would the explicit formula be? Not n plus 6. 6n is part of it. And then, so let's see, if we're plugging in 1 for the first term, we want the first term to be 9. So if I plugged in a 1 right there, what else would I need in order to make this thing equal 9? A plus 3. So that would be our explicit formula for this same sequence. Does that work? If I want, say, the third term, 6 times 3 plus 3, that's 1. Did that give me the third term? Yeah. So they give it, you can have a sequence recursively by defining it in terms of previous terms, or you can have it explicitly by defining it in terms of n. So let's go ahead and try one more recursive formula. Let's do 56. Yeah, let's do 56. Ah, there we go. I can just move that down. No, I can't. That's too big. I'm just going to have to erase some of this. All right, let's do 56. In 56, it says the first term is -3, and they're defining recursively. They're saying the nth term is equal to 4 times the previous term. So again, a sub n minus 1 in English means previous term. We're saying the nth term is 4 times the previous term. A recursive formula, you can only move your way along the sequence 1 term at a time. So like right now, could I right now tell you what the 10th term is? All I know about the 10th term is that it's equal to 4 times the 9th term. That's not very helpful because I don't know what the 9th term is. So, in fact, the only term I actually know right now is the first term. So we call this number your seed number. That number seeds the whole sequence. If I didn't know what that first term was, I would have no idea what any of the terms are. Because again, like right now, if I just ask for the 10th term, all I know is it's 4 times the 9th term, but I don't know what the 9th term is. I don't know what the 8th or the 7th or the 6th term is. I don't know anything. So you need to have at least one term to start the process. So go ahead and calculate out the first few terms. So a sub 2 would be 4 times a sub 1. At least that's what the formula says. The nth term is equal to 4 times the previous term. Likewise, a sub 3 would be 4 times a sub 2. And a sub 4 would be 4 times a sub 3. And so on. That's what it means to do a recursive sequence. So the second term would be 4 times negative 3, which is negative 12. Because the first term was negative 3. And then the third term would be 4 times the second term, which was negative 12. So now the third term is negative 48. And the fourth term is 4 times the third term, and the third term was negative 48, so that's 4 times negative 48. Ooh, which is what?
192.
Negative 192?
94.
94?
Wait.
I need convinced.
Yeah, 192.
Oh. All right. So this is how we do a recursive sequence. I suppose now that we've done a few, we could say, yeah, what we've already said, that a recursive sequence defines the nth term in terms of previous terms, whereas an explicit sequence defines the nth term in terms of the number n, so that you can just calculate it. Again, you might notice if you just took these terms now and wrote them out, the sequence would be negative 3, negative 12, negative 48, negative 192. And just looking at that, it might be pretty obvious what the sequence was. What are we doing to get from one term to the next? What are we doing to get from negative 3 to negative 12 and then from negative 12 to negative 48? Multiplying by 4. And the fact that we're multiplying by 4 each time is where the recursive formula came from. The recursive formula just states, if you want the next term, multiply the previous term by 4. All right, I'll do one more with you from this page. Number 57 is actually the Fibonacci sequence, but with a different seed number. So take a look at this formula. This is the recursive formula. It says the nth term is equal to the previous term plus the previous term. And they're saying to start the sequence off with the numbers 7 and 7. So first let's do this conceptually. They're saying that the first two terms are 7 and 7. A1 is 7, A2 is 7. And they're saying, go ahead and generate the sequence, get the next term by adding the 2 previous terms. So we would do 7 plus 7 is 14, and then 7 plus 14 is 21, and then 14 plus 21 is 35, and 21 plus 35 is 56, and so on. That's what they're saying in this formula. The nth term is equal to the sum of the 2 previous terms. Because a sub n minus 1 is the term before n, and a sub n minus 2 is the term before n minus 1. Does that look like the Fibonacci sequence? It doesn't look like the Fibonacci sequence. What if I divide all those terms by 7? Then does it look like the Fibonacci sequence? Yeah, it sure does. So fundamentally, the fact that this recursive formula is add the 2 previous terms is fundamentally still the Fibonacci sequence, but we've simply multiplied all those terms by, in this case, 7. Now, this, however, you notice both of the seed numbers were the same. They were both the same. What happens if the seed numbers are different? Take a look at number 58. It says now, you'll notice it's still a Fibonacci sequence. You're saying the nth term is equal to the previous term added to the previous term before that. But now I want to seed it with the numbers 3 and 4. So we could do this, again, conceptually. We just start by writing down 3 and 4. And now go ahead and generate this sequence. Add the previous 2. So 3 plus 4 is 7, and 7 plus 4 is 11, and 7 plus 11 is 18, and 11 plus 18 is 29, and 18 plus 29 is 47. Does that look like the Fibonacci sequence? Not really. And we can't just divide everything through by a given number to make it look like the Fibonacci sequence. And that's because we seeded that sequence with different starting numbers. Okay. Well, folks, that's the idea of a recursive sequence. Could you write anything you wanted? Could you say, show me the sequence where you add the previous term plus the third previous term? Meaning you look at the term before it and the term 3 terms before it. Could you do that sequence? Sure. And that might end up being totally different. Like what if I start off with 1, 1, 1, and it says, to get the next term, add the first and third term before it. So now 1 and 1 makes 2, and 1 and 2 makes 3, and 1 and 3 makes 4, and 2 and 4 makes 6, and 3 and 6 makes 9, and 4 and 9 makes 13. It's just another way of making a sequence. So there's a lot of flexibility here. I'm not saying the sequence is interesting.
Wouldn't it be the second term would be 1 plus 1 is 2?
These were my seed terms. I just claimed those to be my starting terms. Yeah. There was no reason it had to be 1, 1, 1. It could have been 1, 2, 3 even. And then from there I could continue the sequence.
How's the second term 1 if the first term is supposed to be the second or the first and the second or the third term added together?
Ah, well, because you need to start the sequence somewhere, right? In order to do a recursive sequence, you need to have some seed numbers. And I just chose to make the first 3 numbers to be 1, 1, and 1. Because that way it'd have material to do this formula with. What are you claiming it should have been?
2.
This should have been 2?
The second term should have been 2. Because
Really?
I'm taking the first term and the third term and adding them? Is that not what the...
Oh, yeah. You're taking the first and third term and adding them to get the next term. You're not adding the 2 numbers around it. You're saying for the, like let's say I want to get the next term. That's what I'm really saying. The next term is add the 1 before it plus the 1, 3 before it. So to get this term, I would add 6 plus 13 to get 19. And in order to do that, I need to have at least 3 numbers already written down. And so I just randomly chose it to be 1, 1, and 1 to make it look like the Fibonacci sequence. I'm sorry, I don't think I was being very clear. Did that answer your question?
Yeah, I'm getting off in the camp now.
Okay. All right, folks. Well, let's go ahead and keep going. Oh, great. Now, well, no, I guess that's it. Let's keep going. This next page. Now, folks, this is an overview of sequences. We're going to see a lot of different things. In terms of sequences and how to write sequences down and how to define them and even how to add them together. So this next page refers to sigma notation. Well, what's sigma?
Sum of things?
What's that?
Is it the sum of things?
Yeah. Sigma refers to taking a sum. And in the Greek alphabet, this letter right here is the letter sigma. This is the Greek letter S. All right, so that's sigma. It's the Greek letter S, and it stands for the word sum, which means to add together. So what we're looking at in these next few problems is they're essentially asking us to add a sequence of numbers together. Don't just write down the sequence of numbers. Actually write the sequence down and then add them all together. So that's what the letter sigma stands for. Now, what does all the rest of this stand for? Let's go ahead and take a look at the first problem pretty closely so we can understand the parts and pieces. We're saying in the number 59 that every term in the sequence has that structure. Okay, so in fact, this is an explicit formula. We're stating that the kth term in the sequence is 2k minus 2. This is an explicit formula, and it's literally telling us how to calculate each term in the sequence. Now you'll notice I'm using the letter K now instead of the letter N. That doesn't matter. You could use the letter K, you could use the letter N, you could use any variable letter that you want. And what we're saying now with this sigma notation is they want us to add together all the terms from the second term all the way up to the fifth term. So they want us to calculate, in this sequence, the second term, third term, fourth term, fifth term, and then add them all together. So I want to show a little work with you folks before we just go ahead and do it. So what would the second term be? Because that's what this sigma notation means. It goes, start from the second term, and then list out all the terms up to the fifth term, and then add them all together. So what's the second term? 2 times 2 minus 2, which is 4 minus 2, which is 2. The second term is 2. And what's the third term, the fourth term, and the fifth term? Go ahead and calculate it. Calculate the second, third, fourth, and fifth term using that explicit formula, 2k minus 2. And so the second, third, and fourth term, second, third, fourth, and fifth term were 2, 4, 6, 8. Is that what you got for the terms? And perhaps that was going to be obvious. How do you get from one term to the next? You're adding 2. And what told you that from the formula? The fact that it was 2k. So we could have known ahead of time that since it was 2 times a variable, we're adding 2 every time. And that we really just had to calculate the first term in the sequence and then keep adding 2, adding 2, adding 2. Well, in any case, let's go ahead and do the problem. Now that we have this nice, simple listing of the terms, sigma from 2 to 5 of 2k minus 2 means literally add 2 plus 4 plus 6 plus 8. And add those together. How can you add all of those really quick without literally going 2 plus 4 is 6, 6 plus 6 is 12, 12 plus 8 is... How could you do it? Yeah, you pair them up again, just like the Gauss problem. You could say 2 plus 8 is 10, 4 plus 6 is 10, that's 10, and 10 makes 20. So the answer to this problem is 20. And that's what all this notation means. Sigma notation means add them up. And the 2k minus 2 is an explicit formula telling you what each term in the sequence is. Before we move on to the next problem, I'd like to go ahead and show you what this might look like if you did it more formally. So everyone, please write this down with me. I'm going to write the problem again. Sigma from k equals 2 to 5 of 2k minus 2. What you could have done is literally written out 2 times 2 minus 2 plus 2 times 3 minus 2 plus 2 times 4 minus 2 plus 2 times 5 minus 2. Is that fair? See what I did? I took the formula and I inserted each counting number, 2, 3, 4, and 5, and I just plugged it into the formula and literally wrote it out. Now you might look at that and say, oh, I don't know, Mr. G, that's, why not just write out 2 plus 4 plus 6 plus 8? But see, we had to do our work somewhere else. So why do our work somewhere else when we can just make our work part of the sequence itself? So now what I'll do is I'll drop down a line. I'll work downward and say 4 minus 2 is 2, and 6 minus 2 is 4, and 8 minus 2 is 6, and 10 minus 2 is 8. And then I can go ahead and write my answer of 20. So I'd like to encourage us to start doing it like that. So it looks really nice. And you can literally see where it's all coming from. So before we go on our break, let's do number 60. Let's do number 60 like that. And I know the problem is already there. I want you to write it again in your own handwriting. So go ahead and write down sigma from k equals 3 up to 6 of the formula, k squared minus 3. And I want you to go ahead and just plug in the numbers 3, 4, 5, 6. And put each term in parentheses. So that would be 3 squared minus 3 plus 4 squared minus 3 plus 5 squared minus 3 plus 6 squared minus 3. Which is a good practice. Instead of doing it all in your head, is showing that work and showing the structure. So now I can calculate each one, still in parentheses or not in parentheses. 9 minus 3 is 6. And then 16 minus 3 is 13. And 25 minus 3 is 22. And 36 minus 3 is 33. Well, add all those together. Is there a clever way to add those? Does adding them in pairs help this time? I don't think so. I don't see a way to add them in pairs. So I'll just add them together. 6 and 3 is 19. Sorry, 6 and 13 is 19. 22 and 33 is 55. 19 plus 55. Yeah, 74. So the answer is 74. Okay, well, we'll take a break. And we'll come back. So what time is it? 9:02? Let's go back at 9:12. Yeah, Jose. Hey, don't go anywhere. I've got a paper. You did? Well, I need you to. Do you have it? You have it? Okay, so you do have one. Okay, so you fill it out and email it to me before the end of today. Okay. And here, I'm going to make it. Jose. Hey, you still around? There you go. Oh, that's you, right? Yeah. Oh, yeah, here, I'll do that. I'll see. All right, thank you. No verify. No evidence. Oh. There you go. Great, thank you so much. Wait, what is it? What is it? Did you not get one? Like a photograph? Oh, how did you know what photos?
Well, it wasn't physical, but it was online.
Oh, okay, so you just copied that and copies on. Okay. All right, folks, I think we're back. Let's go ahead and let's see. And maybe we don't need to do another example of those two because I think I'll leave those for you. So, this next section, if you turn the page, I think you have to turn the page. Did you all have to turn the page to get to here? Yeah. Okay, we're going to treat this as an optional topic. It just so happens that there are particular formulas that exist that allow you to find a sum without actually writing out all the terms and doing it yourself. So, for instance, I'll just do one of these with you. What we have here, and you don't have to write this first part down. Well, let's say that I did write this out explicitly, okay? This sum of 3i, where I'm plugging in 1, 2, 3, 4, 5, 6. So that would look like 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5 plus 3 times 6, and that's it. So that's what my sum would look like. Don't write that down. Now, what do you notice about the 3 all the way across? What could I do with that 3? If I wanted to, I could factor the 3 out, and that would leave me with 3 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And what that means, the fact that I could factor that 3 out, is that I could go back to my original sigma notation, and the fact that there's a 3 being multiplied by the variable I could just put that 3 out in front of the sigma notation. And I could say this sum is actually equal to the sum of I equals 1 through 6 of I. And once I calculate that sum, I can just multiply by 3. So that's the first observation you could make. Like if you want to just somehow start simplifying the process of computing sigma notations, you could notice that you can always pull out a constant. You could just pull that constant right out front and multiply it times the result of whatever you get. And that just simplifies things a little bit. Well, now we have the sigma notation of just the letter I, meaning you're just adding the counting numbers, and you're only going to count them from 1 to 6. Well, that wouldn't be too bad. We could all count that up in our head. But it turns out there is actually a formula, and it states that the sigma of the letter I from 1 to n, whatever number you want to go to, is simply the formula n times n plus 1 over 2. And so in this particular case, I'm going to count from 1 to 6, and so that matches this formula exactly. I could go ahead and just use the formula of n times n plus 1, in which case it would be, since I'm counting up to 6, 6 times 6 plus 1 over 2. And since there's a formula, I don't even have to add up all the terms. What does the formula give me? This is 3 times 6 times 7 over 2. And 2 goes into 6 3 times. And that gives me 3 times 7, which is 21, and 21 times 3, which is 63. So that's apparently what the sum would be using the formula instead of actually adding it together. What if I had added it together? 1 and 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. And 21 times 3 is also 63. So you can see you get the same answer either way. So that's as far as I'm going to talk about right now. I want to consider this an optional topic. That is, if we can get all the way through everything else, and by next class period we're totally done, then we'll come back and we'll take a look at these for fun. But for now, let's go ahead and keep going. Okay, so I think we have a couple word problems here. This first one, is everyone on this page? Let's show the page. So suppose an insect population density in thousands during year n can be modeled recursively by this sequence. Now this is pretty fascinating. This is really interesting. We're looking at the density of a bug. First of all, the density of bugs, that's terrifying to me. At most, how many bugs do you think I hope to have in my bedroom? Hopefully 0, at most 1, right? Isn't that just gross to even think about 1 bug crawling around in your room? But now consider you're talking about the density of bugs in your bedroom. What does that imply? Like 10 bugs in your bedroom, 20 bugs in your bedroom? Gosh, I hope not. But that's what we're talking about. We're talking about insect population density in thousands in a particular area. So hopefully we're not talking about my house, right? Thousands of bugs inside my house. I hope not. Hopefully we're talking about a forest or a field or a city or who knows. So everyone go ahead and write down the formula. It says that the nth term is equal to 2.98 times the previous term minus 0.17 times the previous term squared. That means some scientists put together a model, and that model stated that once you knew how many bugs were in an area in year 1, you could predict how many bugs would be in that area in year 2, which would then predict how many bugs would be in that area in year 3, and so on. And you can tell that they're seeding this sequence with 1, meaning that the density in that area in thousands is 1. That means there's 1,000 bugs in that area in the first year. So how many bugs are in that area in the second year? How do we compute that? I'm letting n equal 2. I'm letting n equal 2. So what would my a sub n minus 1 be? If I'm plugging in 2 for n, then I have a sub 2 minus 1, which is a sub 1. So now we're saying 2.98 times the first term minus 0.17 times the first one squared. And then we'd actually have to plug in the value for the first term. In this case, we know the first term was 1. So that means 2.98 times 1 minus 0.17 times 1 squared. And now we actually have to compute that. So on my calculator, 2.98 minus 0.17. And that states that in the second year, the density is already up to 2.81. And what does 2.81 represent? Thousands of bugs. Yeah, 2.81, thousands of bugs in this particular region. All right, well, how would we compute a sub 3? Now I want to compute a sub 3. What would that formula look like? A sub 3 would be what? 2.98 times the second term minus 0.17 times the second term squared. That's how the formula is working. We're defining the third term recursively in terms of the second term. So now we'd have to plug in all of our numbers and say the third term is 2.98 times the second term, which was 2.81, minus 0.17 times the second term again, which is 2.81, squared. Well, I need a better calculator for this. Not my phone calculator. So what do we have here? 2.98 times 2.81 minus 0.17 times 2.81 squared. And this time I got 7.03. So in general so far, folks, what's happening? A sub 1 was 1, A sub 2 was 2.81, A sub 3 was 7.03. What appears to be happening to the density of bugs in this area? It's increasing, right? The number of bugs is increasing. What will happen in general, though? Will a population of creatures in an area continue increasing forever? No, because eventually they'll run out of resources, they'll start fighting each other, they'll form different political parties, right? In the end, the population will start going down again. We don't know how far down. Now, in this particular case, thank goodness, it says use technology to graph the sequence. So apparently they're not asking us to do this all by hand, 1 through 20. In any case, that's as far as we need to go with this particular problem. We could go ahead and keep on computing this. You could bust out your calculator to do it for you. you could maybe plug it into an Excel spreadsheet, but that's fine. I just wanted to show you that they do sometimes use recursive models to model what happens in the population over time. Okay, so we're done with that. 68. Suppose that a certain bacteria can double their size and divide every 30 minutes. So let's just consider what that means. We start with one bacteria. And then at the end of 30 minutes, how many bacteria do you have?
2.
2. And then at the end of another 30 minutes, how many do you have? 4, right? Because they just doubled. And then at the end of another 30 minutes, how many do you have? 8. And at the end of another 30 minutes, you have 16. So that's what's happening. So we would say that this one bacteria was at time equals 0. And then 30 minutes later, you had 2 bacteria. And 60 minutes later, you had 4 bacteria. And an hour and a half later, you had 8 bacteria. And 2 hours later, you had 16 bacteria. And if you keep on going like that, 2.5 hours later, you'd have 32 bacteria. You'd keep modeling it like this. So it says, write a recursive sequence that describes this growth where each value of n represents a 30-minute interval. So how would we write our recursive sequence? The nth term in the sequence is equal to the previous term, what? What do we have to do to that previous term? Add or subtract something to it, or multiply or divide something to it?
Multiply.
Just multiply. So the recursive formula is simply that the next term in the sequence is 2 times the previous term in the sequence. And that would be our recursive sequence. Not very challenging. And they're saying that our seed number is a sub 1. So the first, at time 0, the total number of bacteria was actually already 451. Well, that's it. They just wanted a recursive sequence. And that would be the recursive sequence. What if the bacteria could triple their size every 30 minutes? What would the recursive formula be?
3 times.
Yeah, just 3 times a sub n minus 1. Or what if I said every 30 minutes, the bacteria colony can have 30 bacteria babies? What if that was the recursive formula? That every 30 minutes, bacteria can have 30 babies. What would the recursive formula be? Yeah. Yeah, exactly. So it really just depends on what you want to say about the particular population and how they're growing. They're either, say, doubling in size, so you take the previous term times 2, or they're simply adding a certain number of people, or bacteria, and so you're adding to the previous term. Okay, well, that's all. So everything that we just looked at, folks, was talking about general sequences. Just how do we talk about sequences in general? And so just to quickly recap everything that we just saw, we had the idea of an explicit sequence. And the explicit sequence was something like a sub n equals 3n squared minus 2n plus 1. An explicit sequence explicitly allows you to calculate the nth term of the sequence by simply knowing the number n. So if you wanted the 47th term in the sequence, I could just plug in 47, and it would calculate for me the 47th term in the sequence. The recursive formula, not so. The recursive formula is like climbing a ladder. You can only get there by climbing 1 rung at a time. You just can't skip. And so you would say something like the nth term in the sequence is maybe 5 times the previous term plus 30. And so you're defining each new term in terms of the term before it, or maybe even many terms before it. Maybe the nth term is actually the previous term plus 3 times the previous term. And that would be an example of a recursive sequence. And then we talked about sigma notation. And sigma notation was a way to simply add up a bunch of explicit formulas, just a way to add them all together. And that was sigma notation. So these are the ideas that we've looked at thus far. What we'd like to do now is consider 2 specific different types of sequences. within the world of sequences, there's two special simple types. And I'm going to go ahead and introduce both of them before we look at either one. The first type is called arithmetic sequences. And in an arithmetic sequence, such as counting by multiples, like 5, 10, 15, 20, 25, 30, in an arithmetic sequence, you're always adding by the same number every time, either adding or subtracting. So you get from this sequence, you're simply adding 5 every time. Very monotonous, you're just adding 5 every time. So in an arithmetic sequence, you add or subtract some number, or we're going to call it D, for the common difference. You're just going to add or subtract some number over and over again. So this is an arithmetic sequence. So is this one. 10, 8, 6, 4, 2, 0, -2, -4. In the first sequence, the common difference is 5. And I would say my common difference is 5 because I'm adding 5 over and over and over and over again. In this sequence, I would say my common difference is -2 because I'm subtracting 2 over and over and over and over and over again. These are both arithmetic sequences. What's the most boring arithmetic sequence you could have? Even more boring, +0. You could theoretically have the sequence 8, 8, 8, 8, 8, 8, 8, and that common difference would simply be 0. It's not very interesting, but it would technically be an arithmetic sequence. Okay, so what could we ask about arithmetic sequences? Well, we could ask, what's the nth term? Right? What's the 100th term in this sequence? Or we could ask, what's the sum? How do we add all of them together? Those are the two basic questions we'll be asking over and over again. What's the nth term? How do we calculate the 100th term without actually having to write it all down and get there? And then how do you add up the first 100 terms without literally typing it into your calculator? So these are the two questions we're going to ask over and over. What is the nth term? And what is the sum of the first n terms? Now, folks, asking those two questions, like let's say I took this first sequence right here, 5, 10, 15, 20, and I asked you to tell me the 100th term. Could you find that out for me? If I said, hey, what's the 100th term? Could you find it out? Of course you could. It might be time consuming. Like worst comes to worst, what could you do? You could just write them all out, right? Worst comes to worst, you could always tell me the 100th term by just writing it all out, but that's time consuming. Also, could you find the sum of the first 100 terms? Could you go ahead and add up the first 100 terms in that sequence? Yeah, you sure could. You could just type it all into your calculator. Worst comes to worst, you could just add them all together and be very time consuming. So obviously, that's not what we're asking. We're not asking, can you do it? We're asking, can you do it quickly, efficiently, and are there formulas? And how can we do this more efficiently than just brute force? We don't want to just use brute force. Okay, sorry, one more. Now that's an arithmetic sequence. What about geometric? A geometric sequence is not one where you add over and over and over again. What do you think? Rather than adding something over and over and over, you're going to multiply something over and over and over again. So in a geometric sequence, you're going to multiply by some number r, and we call that the common ratio. D was the common difference, what you're adding or subtracting. And now in a geometric sequence, we're going to multiply r, and that's the common ratio. Over and over and over and over again, same number. So for instance, you could do a simple geometric sequence of multiplying by 2. So you could just start doubling like the bacteria. 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And in that case, our common ratio would simply be 2. Or you could do a geometric sequence in which you multiply by a fraction. So I could cut it in half every time. So 1 half of 1 is half of a half is a fourth, half of a half is an eighth, half of an eighth is a 16th, half of a 16th is a 32nd, and so on. And in that case, the common ratio is 1/2. So the first thing you might notice is that in an arithmetic sequence, you can add over and over and over, or you can subtract over and over and over. In a geometric sequence, you could multiply over and over and over, or you could divide over and over and over again. Because multiplying by a fraction is really dividing. So we have this idea now of a geometric sequence in which you're multiplying over and over again. And I could ask you the same questions. What's the nth term? So if I said, what's the 100th term in this sequence? What's the 100th term? Or if I said, add them up. What's the sum of the first 100 terms? We want to look at arithmetic sequences, geometric sequences, and ask those two questions. What is the nth term and what's the sum of the first n terms? Again, you could do it all by brute force, but we don't want to do brute force. We want elegance and formulas and simplicity. Okay, so everyone turn the page. Are we on number 69, or do you not have to turn the page? You don't have to turn the page. We're on page 17, folks. So in number 69, I should say we're starting with arithmetic sequences. In fact, that's probably all we'll do today is arithmetic sequences. So today we'll finish arithmetic sequences, and when we come back after Thanksgiving, we'll do geometric sequences. So for the rest of the day, we're doing arithmetic. What is the common difference for the first one? Just one, right? We're just adding one over and over again. So the common difference you would write down is D equals 1. We're going to use the letter D to represent the common difference. And what is the common difference for the next one? 5. Because we're adding 5 over and over and over again. All right, in the next couple questions, it says write out the first n terms of the given arithmetic sequence. So we're assuming the sequence is arithmetic. And the value of n is indicated. So we want a sequence who the first term is 20, and the common difference is 7, and they'd like the first 5 terms. So the first term is 20. I want the first 5 terms. I'm going to go ahead and put a line there to remind myself, okay, I need 5 terms total. And the common difference is 7.
They're not just asking for the fifth term.
Find the first n terms, as in the first 5 terms of the given sequence. So I think we just want the first 5 terms. Yeah. Okay, the common difference is 7. So it'd be 20 plus 7 is 27, plus 7 is 34, plus 7 is 41, plus 7 is 48. It's pretty straightforward. This is very simple. The key is to be able to look at something like this and know what they're saying, right? Because now they took away all the words and they're just telling you, okay, we're talking about an arithmetic sequence. We know the first term is 1, so, and we also know that the common difference is 5, and we want 6 terms. So I'm going to start with a 1, second term, third term, fourth term, fifth term, sixth term, and you'll go ahead and start generating that sequence by adding 5 every time. So 1 and 5 is 6, and 5 is 11, and 16, and 21, and 26. So these problems aren't at all hard. They're just teaching us new vocabulary. So we all know for sure, we already know the subscript notation for a sub 1, a sub 2, but now we know that D means the common difference of what you're adding or subtracting by every time. And N is telling us how many terms in the sequence that they want. Oh, Xavier, I get your question. You were saying, were they asking for the 6th term?
But they weren't.
Okay, yeah, but they weren't. But nevertheless, we did find the 6th term.
Yeah.
Yeah, okay. All right. So continuing on, I don't think I'll do all of these with you. I'll skip 73. Well, let's just go ahead and take a look at 74 in any case. How do we do number 74? We know that the third term is 4. So hold on a second. The first term we don't know. The second term we don't know. But the third term we know is 4. And then the fourth term, fifth term, sixth term, seventh term, eighth term. What are they really asking? They're telling us that the third term is 4. The common difference is 2. But what does n equals 5 mean again? They want the first 5 terms. That's what they want. They want n equals 5, meaning they want the first 5 terms. So what are the first 5 terms? The common difference means subtracting 2 to the right. Right? As we continue to generate this sequence, we're subtracting 2. So 4 minus 2 is 2 is 0. I'm sorry, 4 minus 2 is 2, and 2 minus 2 is 0. And the next term, if we did go that far, would be negative 2. And the next term, if we did go that far, would be negative 4. What were the first couple terms? Yeah, 6 and 8. Because even though it says the common difference is subtracting 2, that means we're subtracting 2 to the right, but we're actually adding 2 to the left in terms of generating our sequence. So this way, we're subtracting 2, and this way, we're adding 2. So technically, all I wanted was the first 5 terms. Okay. This is just kind of getting to know sequences. Remember, the 2 questions we want to ask is what's the nth term and what's the sum of the first n terms? So our first question is, what is the nth term? And fortunately, there's a formula for it. And the nth term is equal to the first term plus d times n minus 1. So everybody, let's write that down in our own handwriting. For an arithmetic sequence, the nth term, this is an explicit formula. This is an explicit formula for the nth term. Is the first term plus the common difference times n minus 1. Note that this is not d sub n minus 1. This is not a subscript. This is literally the common difference times the n value minus 1. So we're actually going to subtract n minus 1 and multiply by d. Whereas that's a subscript, and that's a subscript. So note the instructions in this problem. It says find a sub n, meaning find the formula for the nth term. So here's our general formula for the nth term. And it also says find the 6th term for the following arithmetic sequence. Well, we could probably go ahead and find the 6th term right now. What is the 6th term? What are we adding by? 8. So first, second, third, fourth, fifth, 6th term would be 42. So we already know the answer. The 6th term is 42. We can just do that casually. But now let's do the actual formula. How would we find the formula for this sequence? Well, plugging in what we know, the nth term is equal to the first term, which is 2, plus the common difference, which we just said was 8, times n minus 1. That's the formula for the nth term. It's just the formula. So forever now, if you wanted to find any given term in that sequence, like a sub 100, if you wanted the 100th term, you could just plug in 2 plus 8 times 100 minus 1, and you can actually calculate what the 100th term is, which would be 894. Well, they weren't asking for the 100th term. They were just asking for the 6th term. So let's check to see that our formula works. The 6th term would be 2 plus 8 times 6 minus 1. So 6 minus 1 is 5. 5 times 8 is 40. And 40 plus 2 is 42. And did that agree? Yeah, it gave us the 6th term like we expected. So that's a pretty powerful formula. This formula will work for all arithmetic sequences. To a certain extent, you might say, well, it seems like we've answered the first question. What is the nth term? Yeah, that's the nth term. That formula will tell you the nth term. Okay, so you can go ahead and do number 76. Number 77, I think you can go ahead and do number 77 as well, because they're still asking for the same thing. They want the formula for the nth term, and they want the 6th term. So everyone go ahead and do 76 and 77. Let's go ahead and do those two before we move on. Yeah, go ahead and work on them right now. So for the first, number 76, Aldo, what was the common difference?
4.
Yeah, the common difference was 4. And what did you write down for your formula, Brendan?
For
Number 76.
6, I did AN equals 2 plus 4, and then in parentheses 6 minus 1.
Oh, okay, so that's for calculating the sixth
Yeah,
term.
yeah.
Yeah, okay, so that would be the general term. And then what did you actually get for the sixth term, Kumar?
22.
42? Was it 42 again?
No, 22.
Oh, 22. Okay, 22. Thank you. All right, folks, so check your work. See if you got 22 for those. Which I think works, because if you plug in 6, you'd have 6 minus 1 is 5, 5 times 4 is 20, and plus 2 is 22. So that works. Do things change remarkably when the common difference is negative? It's still basically the same, right? So we know that we can go and write down our formula. A sub n is equal to the first term plus d times n minus 1, and in this case, d was negative. So if we simplify that, that's 42 minus 8 times n minus 1. And then we plug in our 6, so the sixth term is 6 minus 1 is 5, times 8 is 40, 42 minus 40 is 2. Did everyone get 2? Oh, good. All right. Now, folks, you might be wondering, do we need to simplify this? What do you think? Should we simplify that? Can it be simplified? It surely can. We could distribute the 4, right? And then combine like terms. So this could really be 2 plus 4n minus 4, which would really be 4n combining like terms, 4n minus 2. Should we simplify? I mean, I guess you can. Does it make our life hugely better to simplify? Not really. I mean, you could say that this formula has 3 computations. You have to subtract, multiply, add. Whereas this one, you just have to multiply, subtract. But honestly, the first computation is just minus 1. It's really not that hard of a computation. So you could argue that simplifying takes more work and really doesn't save you any. So I think we're all fine with just leaving the answer as it is in terms of the actual formula. You know, why not? Okay, let's keep going. That was our first question, is find the nth term. The second question was, what is the sum of all of these terms? And the first thing I'd like you all to notice is go ahead and write it down in your own handwriting, the formula. The sum of n terms, that's how we write it down, the letter S with a subscript n. The sum of n terms is n halves of the first term plus the last term. And if you want to write that out in English, that wouldn't be a bad idea. You could write first term plus the last term. That's our formula for finding the sum of any sequence. The actual sum, like the sum if you add up all the terms
Of any like explicit.
of any
mathematics
sequence.
in general.
Yeah, in general. It doesn't matter if the formula is given as explicit or recursive. So long as you know the first term and the last term and how many terms there are, you can add them up. Yeah. So for folks, the first thing I'd like you to notice is that this formula makes a lot of sense, and we've actually already seen this formula once today. Where have we already seen this formula? Remember the Gauss problem? The Gauss problem was to add up all the numbers, 1 plus 2 plus 3, all the way up to, oops. Yeah, all the way up to 100. And what was the trick for solving that problem? You put the numbers into pairs, so you added the first plus last term to get 101, and you keep on pairing up the numbers, and since there were 100 numbers, how many pairs were there? half of that. And that's what this formula states. You take the total number of numbers and divide it by 2, and that tells you the number of pairs. And then the first plus last is telling you the sum of the first and last, and then the second and second to last, and the third and third to last. So this formula is the formula that allows you to add up this sequence very quickly. That was the Gauss problem that we saw. So that's how this formula works. If you want the sum of any sequence, you pair up the numbers from the beginning and the end, and then you count how many pairs there are, which there's always n divided by 2 pairs. There's half as many pairs as there were numbers. All right, so there's our formula for finding the sum of an arithmetic sequence. How do we then find, what does it say? Find the sum of the first n terms of the following sequence. They want us to find the first 4 terms. Now, finding the first 4 terms, this would be pretty easy. Do we need a formula for this? It's just 4 terms. If the first term is 5, and the common difference is 5, meaning I'm going to add 5, add 5, add 5, I could probably just add those. I don't need a formula, right? So 5 and 15 is 20, 10 and 20 is 30. The answer should be 50. But nevertheless, we'd like to see how to actually use this formula. Okay, so let's go through the mechanics of how to use the formula anyway, right? So in our formula, we're going to find the sum of the first 4 terms, which means we can go ahead and put in 4 over 2, and we already know the first term, which is 5. So just reading the problem statement got us most of the way there. We saw how to plug in all of our numbers. We're finding the sum of the first 4 terms. We plug in 4 for n. They already told us the first term. So what do we still need to calculate? The last term. Yeah, the 4th term. So to do that, we actually need the formula a sub n equals a sub n, 1 plus d times n minus 1. We need to use our explicit formula to calculate the last term. So the first thing we need to do is write down our formula for any given term, for the nth term. Plug in our information. So in this case, the nth term is 5 plus 5 times n minus 1. And what we really want is the last term in this sequence, which is the 4th term. We want the 4th term in this sequence. So I'm going to let n equal 4. So the 4th term is 5 plus 4 minus 1 is 3. 5 times 3 is 15. The 4th term is 20. Is that true? Was the 4th term really 20? Yeah. So now we can go ahead and use our handy-dandy sum formula to find the sum that we already knew because it's so short. But does this really give us the correct answer? 4 over 2 is 2, 5 plus 20 is 25, and 2 times 25 is 50. So yeah, the formula works. Now I realize in a problem like this, you would say, Mr. G, I'm just going to add them up. It's so easy. I'll just add them up. But on the test, I'll make sure to make this n value much bigger so that you're not tempted to add them all up, and to make sure that you actually do use the formula to add them up. So let's try number 79. Hold on. Yeah, let's try number 79. And number 79, again, they're only asking for 5 terms. So you could probably just add these up yourself. You could probably just say to yourself, well, the first term is negative 12, and my common difference is minus 1, so I'm just subtracting 1. So my first 5 terms would be 12 minus 1 is negative 13, minus 1 is negative 14, minus 1 is negative 15, minus 1 is negative 16. There's my 5 terms, and I'll just add them up. And you could do that pretty quickly with or without a calculator. So 12 and 13 and 14 and 15 and 16, I already have the answer, and it's negative 70. And that's a fine way to check your work if you like. But what I want us all to do right now is actually use the formula. So we go ahead and write down the Gauss formula. The sum of the first n terms is n over 2 times the first term plus the last term. And what we already know for sure is that we're adding up the first 5 terms. So we're doing the sum of the first 5 terms. N is 5. The first term they told us is negative 12. And what we don't know yet is the last term. This might seem a little ambiguous, a sub n. A sub n does represent the nth term, but in this case it's representing the last term in the sequence. Because what does n represent? N is 5, so that's really a sub 5. We're actually doing the first term plus the 5th term, because we're letting, 5, n equal 5, so that's the 5th term. Okay, so now we have to go find the 5th term. We write down our formula, a sub n is a sub 1 plus d times n minus 1. In this case, the nth term formula is negative 12 plus negative 1 times n minus 1. So that's our nth term. Well, we want to find specifically the 5th term. So a sub 5 is negative 12 minus 1 times 5 minus 1, which is what? 5 minus 1 is 4. 4 times negative 1 is negative 4. Negative 12 minus 4 is negative 16. Is that the 5th term that we expected? Yeah, that was the 5th term that we expected. So now it's negative 16. And now we can go ahead and do this calculation. What's worrisome about this calculation? We're trying to find the sum of a bunch of whole numbers, and yet the very first term that we have here is 5 halves, which is 2.5. Does that worry us, that the sum is going to be a decimal? Because the sum shouldn't be a decimal. We're definitely adding together a bunch of whole numbers, so the sum should be a whole number, and yet I have a decimal in here. Does that worry us? No, because what do we notice about what's happening in here? The sum of negative 12 and negative 16 is an even number, and so that even number is going to balance out the 0.5 and turn it back into a whole number. And so what's our answer? The sum of the first 5 terms is?
70.
Yeah, 70. 28 times 2.5 is? Oh, negative 70. So it worked out. Now there's a chance that you're sitting there saying, hey, wait a minute. If the formula is a sub 1 plus a sub n, but I have a formula for a sub n, why not just combine the two? Why am I coming over here to do all this extra work when I can just put this formula inside that formula and maybe make it simpler? Were you wondering that? Maybe. Like, let's just try it and see what it looks like. The sum of the first n terms of n over 2 is the first term plus the nth term, but the formula for the nth term is a sub 1 plus d times n minus 1. Is that fair? We can just plug that formula in for a sub n, and then we don't have to do that extra step of calculating a sub n, it's just there. So what would that give us? The sum is a sub 1 plus a sub 1, that's 2 a sub 1s, plus d times n minus 1. Well, does that really make life better? I don't know. I don't know if it makes life any better by having that formula written out like that. Because even though now we can just plug in our numbers and it would give us the sum, it loses all of its appeal as an intuitive formula. Right now, this is an intuitive formula. It's the Gauss formula. You add the first and last term and multiply by how many pairs of numbers there are. That's a nice, elegant formula that you can memorize. Whereas writing it down like this, it just lost all of its appeal. You take double the first term, and you add the common difference by 1 less than how many terms there are. This no longer is very appealing as a formula. It loses some of its elegance. Could you memorize that formula if you want to and use it on the test? Yeah. Yeah, you could. It'll get the job done. But I don't think it's as appealing as the first problem or as the first formula. All right. So turn the page. Oh, no, you don't have to turn the page. Okay, it's asking for more sum evaluations or sigmas. I think the reason they're asking for this, because we've already done some sigma evaluations, is because these are, in fact, arithmetic sequences. These are arithmetic sequences. You can tell they're arithmetic because the explicit formula that's in the sigma notation represents an arithmetic sequence. What are we adding by over and over here in this sequence? We're adding by 8 over and over again, because the number being multiplied by the variable is 8. So I know that in this sequence, I'm just adding 8 over and over, so it's arithmetic. Likewise here, the number in front of the variable is a 1, so I'm just adding 1 over and over again. So both of these sequences are technically arithmetic. And so instead of writing this out, and in fact, I'll demonstrate this one. This would be miserable, wouldn't it? If you actually had to add up the first 13 terms using sigma notation, that would look like the first term, 8 times 1 plus 7, plus the second term, 8 times 2 plus 7, plus the third term, 8 times 3 plus 7, and all the way up to the last term, 8 times 13 plus 7. Wouldn't it be miserable if you actually had to type all that into your calculator or actually calculate all that? That would be no fun at all. Whereas what could we do? Since this is the first term, and this is the last term, what can we do instead?
Formula.
We can just use our formula. So the first term, let's go ahead and calculate it. 8 plus 7 is 15. And our last term, 8 times 13 is 80. 104, 111. We should probably check that before we go getting the wrong answer. 8 times 13. Yeah. And we also know how many terms we're adding up. How many terms are we adding up? 13 of them. So we can go ahead and instead of evaluating all of that sigma notation, we can use the sum of the first n terms as n over 2 times the first term plus the last term, which in this case, the sum of 13 terms is 13 over 2 of the first term, which is 15, and the last term, which is 111. Well, that's a significant savings, to be able to find that sum without actually writing down all those terms and adding them all together, but instead using the Gauss formula. I keep calling it the Gauss formula. No one really calls it the Gauss formula. I'm just calling it that because it goes back to the story of Gauss as a child adding up all those numbers. So what do we have? 15 plus 111 times 13 divided by... What did you get?
819.
Yeah, 819. That's our sum, 819. So here's the real question. Given any sigma notation, like if someone gives you a sigma notation with a formula, how do you know when you can use this formula and when you can't? You can only use this formula when we're talking about arithmetic sequences. And what do arithmetic sequences look like? What do the formulas look like? I mean, based on just these two, both of these are arithmetic. What would you say about arithmetic explicit sequences? What do they look like? What does this remind you of? 8j plus 7. It looks like a... Yeah, it looks like a linear equation, right? Doesn't it look like mx plus b? That is mx plus b. And in fact, that's what all arithmetic sequences are. All arithmetic sequences are given by an nth term formula of mx plus b. So that's something that you can keep in mind. Any arithmetic sequence is given by a linear equation, which is mx plus b. So if you want to find the sigma notation of a formula, and that formula happens to be of the form mx plus b, that tells you it's an arithmetic sequence, which tells you you're allowed to use this formula. Yeah, Xavier.
That's what I asked earlier. So it's saying like that sequence, that formula is only for arithmetic explicit.
Okay, yes. I see what you're saying now. Absolutely. This formula is only for arithmetic sequences, which can be written explicitly as mx plus b. But you can also write recursive. You can write arithmetic as recursive. After all, the recursive formula, let's say you had the recursive formula of a sub n is equal to the previous term plus, in this case, 8. So that's a recursively written formula, but that is nevertheless arithmetic. because you're just taking the previous term and adding 8, and then taking the previous term and adding 8. So you really are still doing an arithmetic sequence, even though it's written recursively and not explicitly. So I'm sorry, I misunderstood your question last time. You can use this formula when it's arithmetic, but an arithmetic sequence could be written explicitly or recursively. The key is that it's arithmetic. Does that answer your question?
Yeah.
Okay. Yeah. All right, folks, I'm going to leave number 80 for you. And let's go ahead and do some word problems. Oh, good, because then that'll round out the day. And then the next time we'll do geometric sequences rather than arithmetic sequences. So that first question there, I bet all of you got really excited about. You're all so excited. Oh, like, ooh, I can do that. I can add all the numbers 65 plus 95. And I bet you already have a clever way to do it, other than typing it into your calculator. By the way, should any of you type that into your calculator? 65 plus 66 plus 67, 68, 69. No, that'd be terrible, right? That'd be awful. So instead, how could you do this problem conceptually? Like you could start by writing out 65, 66, 67, and then it's going to go all the way up to 93, 94, 95. And then you could do the Gauss trick, right? Where you're going to add up pairs of numbers. So you'd say you add the first and the last one together, which is what? 95 plus 65, so that's 160. And if I add the second to the second to last, what's that? Better be the same thing, 160. So every pair of numbers is going to add up to 160. But now we're left with a question, how many pairs are there? Can you just subtract 95 minus 65 and get 30? Are there 30 numbers?
No, it's 30.
Hmm?
No, I'm looking at 30 terms.
Oh, are there 30 terms? Are there 30 terms, folks? Which would be 15? Yeah, so the question is, are there 30 terms? This might feel so obvious that you're like, well, of course there's 30 terms. But are there 30 terms? How would we check? Would you count them out? 65, 66, 67, 68, 69, 70, 71, 80, 1, 2, 3, 4, 5, 6, 7, 8, 9, 90, 91, 92, 93, 94, 95. How many terms were there? 31 terms. Did I mess up? Did I just count on my fingers wrong? How many terms are there from 65 to 95? How can we find out? How do we know for sure? First of all, how many terms are there from 1 to 100? This is not a trick question. How many terms are there from 1 to 100? 100 for sure, right? Because that's the first one, so that's 1, 2, 3, 4, all the way up to 100, so for sure. But what happens if I subtract 100 minus 1? It's only 99. So can you just subtract the last number minus the first number to get the number of terms? No. What do you really have to do? Last minus first, and then add 1. So the number of terms in a sequence, in an arithmetic sequence, that is in counting numbers. If you want to know how many counting numbers there are, so let's write it down. Number of counting numbers is what? What would be our formula? Last minus first plus 1. So how many terms are there actually between 65 and 95? 31. That wasn't very obvious at first. It still kind of weirds me out that you have to add 1. So now we know, though, that the first and the last number adds up to 160, and the total number of numbers are 31. So how many pairs are there? How many pairs of numbers are there? 15 and a half. Boy, that's really unfortunate, right? This really messes with our mind a little bit. We have 15 and a half pairs. What does that mean that there are 15 and a half pairs? For instance, I'll give you an example. Here's a list of numbers, 1, 2, 3, 4, 5. How many pairs of numbers are there? There's 2 pairs and a half pair, right? So that's possible. You could have 15 and a half pairs because there's going to be a lone number in the middle that didn't get paired with anybody. Okay, so are we ready to calculate the answer to this problem? I think we are. We now know, let's go ahead and write out the formula. S sub n equals n over 2, and a sub 1 plus a sub n. We'll do the sum of 31 terms is 31 over 2, the first term 65, plus the last term 95. What did we get? What was the answer? Yeah, 2480. 2,480. That's surprisingly large. I wasn't guessing that that sum would be so big. Folks, while we're at it, I have a bonus question for you. Here's a bonus question. How many terms are there from 2 up to 100? What if you count by 2s? How many terms are there now? When it was 1 through 100, it was 100 terms. But now we're only counting the even numbers, 2 through 100. So how many terms are there? 50, right? Because we're only counting the even numbers and not the odd numbers. So it's 50. But what's the formula now? It's not just last minus first plus 1. Because if it was last minus first plus 1, that would imply that there are 100 minus 2 is 98 plus 1, 99 terms. And are there 99 terms? No, there's definitely 50 terms. So what do we have to do? To our formula, last minus first plus 1. To make it give us the real answer. How do I turn 100 minus 2 plus 1 into a real equation that equals 50? Any thoughts? Yeah, divide last minus first by 2. Because then 100 minus 2 is 98, and 98 divided by 2 is 49, and 49 plus 1 is equal to 50. Now, why does that work? Aaron, how did that come to you? Yeah, that's true. You're taking half the terms, so you're divided by 2. Here's another way you can consider it, folks. The numbers 2, 4, 6, 8, and 100, that's actually 2 times 1, 2 times 2, 2 times 3, 2 times 4, and 2 times 50. And if I look at the numbers 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 50, what if I just don't say the 2 times? This is the number 1, 2, 3, 4, and 50. How many terms are there from 1 to 50? How many terms are there from 1 to 50? Well, last minus first plus 1. So the last term is 50, the first term is 1, and 50 minus 1 is 49, plus 1 is 50. So yeah, you take the last minus first and divide by 2. So everyone, please write that down. We already wrote down that the number of counting numbers is last minus first plus 1. But this is a pretty valuable formula we just came up with. The number of terms in general, number of terms, is last minus first divided by the common difference plus 1. That will tell you how many terms there are in the sequence. Yeah, that'll just tell you the straight up number of terms, which might be helpful to know for some of these problems. How many terms are in the sequence? And that formula will work even if you're counting by a certain number, like 3, 6, 9, 12, counting by 3s or counting by 5s. Okay, let's keep going. Number 83. A man earned $3,000 the first year he worked. Well, I hope that was a long time ago. That'd be rough, unless it's just a part-time job and you're just, working on Saturday for 1 hour. I suppose that's not bad. So a man earned $3,000 the first year he worked. If he received a raise of $600 at the end of each year, what is his salary during the 15th year? So you could just try solving it, right? You could just forget all these formulas we've been talking about and just try solving it. What would be an intuitive thought for how much money he's making during the 15th year? Because how much did he make the first year? 3,000. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How about the 15th year? How much would he be making? What would you do with that 600? Multiply by what? Multiply by 15 and then add it to the original? Well, let's try it. What if we did the 600? 600. Whoops. Hold on, we'll finish these. If you take the 600 times 15, that'd be 9,000 plus the original 3,000 is 12,000. Is that the right answer? Was he making $12,000 in his 15th year? Just thank you for guessing. I don't know if 15 was correct. Is 15 correct or is 15 not correct? How many raises did he get? He got 14 raises. The first one, and then the second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11, 12, 13, 14. He actually only received 14 raises. Even though it was the 15th year, he only got 14 raises. So instead what we would do is do 3,000 plus 600 times 15 minus 1 raises. Now, of course, now look at that formula. What does that remind you of? This is literally a sub 1 plus the common difference of n minus 1. You see, it's exactly the same formula that we've been working with. And the key there was noticing that in the first year, he didn't get a raise. It was 3,000 the whole year. Okay. Well, let's see. Number 84 and I think 85. Those are fairly similar problems. Let me just ask a quick question about number 85. It says John does 8 push-ups on the first day and then increases the number of push-ups by 3 push-ups a day. Do you think that's possible? Do you think that if everyone in the room, if we all just dropped down and did 8 push-ups today, do you think that every day you could tack on 3 more push-ups? Do you think strength grows that quickly? Maybe. I've got 1 head shake yes and 1 head shake no. This would be a really fascinating experiment. Now you might be saying I can't do 8 push-ups. Like what if we started with 5 push-ups today? Do you think if we all did 5 push-ups today and then tomorrow add 3 and do 8 and the next day you do 11 and the next day you do 14? Do you think it's possible? Aaron says it's possible. I like that optimism. Everybody, I think this would be fascinating to try. In any case, that's the problem. All right. I think we're going to stop there for today because I think class is over. Well, we have a couple minutes left. The rest of those word problems are for you to try. And let's see, you're all here, so you all turned in your midway quiz. So thank you very much. As far as next week goes, next week. Oh, did I give you your practice test yet? I meant to give you your practice test. I'll have to post it online. Yeah, let me just check. I don't think I have it with me. No, I don't have it with me. Okay, well, I'll have to post that online so that if you want it immediately, you can go ahead and download it. Otherwise, the next time I could give it to you is on Monday, but then it's due on Wednesday. And that's a pretty fast turnaround, isn't it? Let me just double check here. Where is my calendar? Oh my goodness. Oh, there's the calendar. Yeah, so here we were November 22nd. When you come back next week, we have class and then the practice test. Okay, so folks, I'm going to email that to you today. I'm going to email it to you today. Sorry, you'll have to print it out. It's like 8 pages long, I think. But otherwise, I will bring photocopies on Monday, but that'd be a real short turnaround. So everyone, please check your email today, and I'll give you your practice test online. All right. I think I signed in for you. Plus they were taking, right? Yeah. Did you turn in all your papers?
Oh, yeah.
Okay, great. Thank you, sir. Yeah. Oh, no problem. Hey there, Carlos.
I have a question.
Yes, sir.
So I forgot how to practice that send
Okay.
I was wondering if I could send you.
Oh, you mean the stuff that's due today? You mean the midway quiz?
Yeah.
And the extra credit?
Yeah.
Yes, you can send me a picture.
Okay, great.
You're welcome.
Do you think we'll have time to go back to section 5? We never went back.
The 3 variable equations? I don't think we will. It was an optional topic. It's not covered in the final exam. Now I realize that doesn't necessarily, by definition, mean that it's an optional topic, but